To me, it seems very natural to lump composite functions in with the study of functions. Why not? It's about functions. And composite functions are combinations of functions where you have one function inside of another, sort of nested inside. Now, you can actually have more than two of these nested inside one another. You have one inside another, inside another, inside another. Kind of like those Russian dolls that come in the eggs, where you keep opening each one, there's another one inside, a smaller one inside. Okay, so let me introduce this with an example. And let's see, come up with f of x equals to 1 over x minus 2. And g of x is equal to x squared minus 1. All right. Nothing special about those. I just made them up at random here. Now then, to show you what a composite function looks like, let's first think about f of g of 3. Okay. So if the f wasn't there, if you're just looking at g of 3, what does g of 3 tell you? The g of 3 part says to plug 3 into the g function, and we would get 3 squared minus 1, so we're replacing x with 3. So g of 3 is 3 squared minus 1, which is 9 minus 1, 8. You get 8. Now what the composite function is telling you to do is to, in this case, plug 3 in the g function, then take that output, which is 8, and now make it the input of f. So now we'll take this 8 and we'll plug it into f of x, and we get 1 over 8 minus 2, which is 1/6. Okay, so there's that. Let's reverse that process and think about g of f of 3. Now, I always like this because people in algebra get so used to things being commutative. When it looks like you're multiplying, it seems like you just can reverse multiplications anytime you want to. Well, for one thing, this is not a multiplication, and we'll see that we can't reverse g and f here and expect the same result. It's a non-commutative process. All right, so anyway, we'll look at it here. F of 3, if I plug 3 into the f function, then I get 1 over 3 minus 2. Now this is 1 over 1, which is 1, so I get g of 1. And then I'll take that output of 1 and plug it in the g, and I get 1 squared minus 1, which is 0. So here, f of g of 3 was 1/6. G of f of 3 is equal to 0. So we did get a different result when we switched the order of the composition. And that's actually pretty normal for that to happen. Most of the time it does. Now when you get the same answer, regardless of the order, that's very interesting. And we'll look at those in the next section. And the next topic. So that becomes actually quite interesting when these do equal to each other, no matter what number you plug in. So anyway, composite functions, what good are they? Well, it's a process that is sort of broken up into two pieces here, the way this is illustrated. And there are a lot of things in mathematics that do work that way. And now, in calculus, if you take that, then you'll certainly encounter composite functions. The idea of this is included in what's called the chain rule. It's a very important aspect of differential calculus that you have to learn about. So, but in a sense, if a process is broken up into several steps, that could, in a sense, be simpler, couldn't it? So it's like we broke this process up into two separate steps. But if I reverse that process, I don't expect the same answer. Now I should tell you. Let me work these in a more general sense here, and then I'll I want to compare my notation with what your regular textbook is showing you. So I want to ask this question: what is f of g of x?